Testing on YouTube, testing on YouTube. Testing on YouTube. Testing. Testing, testing. All right, YouTube is working. Now, let's go on X and test that. Testing on X. Testing on X. All right. It works on X. Perfect. I don't even check Twitch anymore. Even though it still shows that occasionally people follow me, which is strange. All right. Let's turn off this YouTube just so it's not in the background. How's it going, Pratik? Testing, testing. All right, let's go ahead and get started. We're doing the Horn of Gondor today. Alrighty. That one actually has a smaller mouthpiece, so I can do it longer than the larger mouthpiece of the didgeridoo. Let's go in Open Room XYZ. It's not technically a new horn. I've had that one for a second now. It's been on a couple other streams, but it doesn't quite have the deep resonance of the didgeridoo. All right. Today's stream is called Scaling Synthetic Data. Nice little thumbnail here. This one was actually Flux as well. I've been trying out a bunch of different image generation models for my thumbnails. Pretty much all my thumbnails are one-shot generated now, where I just type in a prompt with the title and it gets it perfect every time now. You know? I remember even just a year ago, you couldn't do this. A year ago, I had this kind of like complicated pipeline where you basically like had segmented things and then you like put the text on and, you know, you still basically had to like kind of have a workflow in order to create a thumbnail. But now pretty much all the state-of-the-art image generators will one-shot a fairly complicated thumbnail with the text perfect. So pretty amazing. How's it going, Mark B? Lessons from scaling synthetic data for trillion scale pre-training. So this is from the Datology AI team. Kind of a weird name. Probably not good for SEO here, but you know, let's actually see if we look at this. So here's the team. I kind of like these team sections like this where they kind of just, rather than just cramming 50 people here into the title page, they keep the title page just the abstract and then the figure one, and then they kind of cram all the names here so that you can actually see kind of the breakdown. But yeah, I would say this is a fairly large team. So what is Beyond Web about? Beyond Web is a synthetic data generation framework that produces high-quality synthetic data for pre-training. Okay. 7.7 times faster than training on open web data. And ultimately, the conclusion of this paper is that there's no silver bullet for generating high-quality synthetic pre-training data. So maybe let's talk about what the hell is pre-training data. So pre-training data is basically internet scraped data sets. It's effectively the largest source of data that you can gather that is in the text modality. And pre-training on internet data is kind of what started this entire AI hype cycle, right? Where people realized that if you could just increase the size of the model and then train it on a massive data set of scraped internet data, you got this kind of almost like AGI-ish intelligence that was, it's still hallucinated, it has all kinds of problems, but it has this just ridiculous generalizability to pretty much anything, right? You can ask it poetry, it can tell you about medicine, it can speak French, right? No other model was able to do that, and that really came from this unlock of using internet scale data. But kind of in the 5 years since we started this new hype cycle in AI, we've kind of started to encounter this kind of data wall, which is basically that we've effectively run out of internet data to search. How's it going, Ed? And this predictable recipe where we were training ever larger models on exponentially larger internet scraped data sets has kind of started to lose steam, right? And I think people have tried different ways of getting more data in, right? So the popular thing right now is reinforcement learning, where you're effectively creating synthetic data, but you're creating synthetic data from interacting with an environment, right? So reinforcement learning is a way to get infinite data by creating an environment and then having an agent that operates in that environment, and then in that way you can effectively collect infinite data. But it's also the quality of the data. There's just something missing there, right? And we're all kind of aware of this, that, hey, even if you collect 10 trillion games of Go or 10 trillion math problems that have been kind of created and then filtered with RL environments, it's not quite the same thing, right? You're never going to get that same pop that you got from the original kind of internet scrapes of the early 2020s. So data quality matters. Rephrasing high quality data provides benefits over using lower quality sources. Distributional style matching is important. Web data contains only 2.7 conversational content, despite chat being a major inference use case. So these guys are going to be creating not synthetic math data, not synthetic Go data, right? These type of like RL-ish type synthetic data generation strategies. They're going to be trying to create synthetic internet pre-training data, which is really kind of where it all came from. So they're doing different strategies for this. And you're going to see that one of the big ones that they do here is basically rephrasing, where they try to take some existing, what they call seed data, right, which is the actual original kind of maybe blog post about, I don't know, bears, or a blog post about dinosaurs, and then trying to rephrase it into maybe a conversation, So, hey, rather than just this generic blog post about dinosaurs that we just kind of feed into this next token prediction during pre-training of our autoregressive transformer, we're going to instead rephrase that same exact blog post as a conversation between two people about dinosaurs. So all the information is kind of still the same, but the words, and more importantly, kind of the tokens and the kind of distribution of those tokens is different than the original dinosaur blog post. So kind of starts to sound a lot like data augmentation, right? Open Room XYZ. We should sample your horns and create neural network clones. Yeah, I mean, maybe I need to sell the entire Hoopo horn collection as like a collectible set. How's it going, Doga? All right. Diversity in generation strategies is critical to leverage continued benefits from synthetic data. We're going to see here that variance and diversity is kind of a very important part of understanding data quality, right? Let's go here. Largely consistent across different rephraser families, rephrasing is a generic capability, and rephraser model efficacy is difficult to predict. We observe diminishing returns when increasing rephraser size beyond 3B parameters. So this was a finding in this paper that I didn't necessarily agree with, and we're going to get into it later. They have a whole section on this, but to me, they found that for the size of the model that they use for this rephrasing, right? So converting the blog post about dinosaurs into a conversation about dinosaurs, they found that it doesn't actually matter. You can use an 8B model and a 3B model, and they both are about the same in terms of generating a variant of your original seed data that is effective in improving the intelligence of the model that you train it on, right? I don't know if that's necessarily true, and I feel like maybe the hidden story in this is that there's probably some way to use RL to hill climb this rephrasing task, right? Because it's a measurable and quantifiable task, right? You can say, hey, here's 4 different models. They're all going to rephrase this original seed data, and then we're going to see of those rephrasings which actually end up being the most useful for creating a smartest model. So that means that there's a way to take that and then use it to improve the rephraser model. So this might be a future here, right? Some kind of future where we have kind of superhuman rephrasers that go through the internet, and every single new piece of data that comes out, they rephrase it 20 different ways, and then we train on that. Okay. Naive approaches to synthetic data generation can provide little benefit or even some detriment while also incurring substantial computational cost for generation. Okay. So the internet, right, there's some cost to that where you have to usually basically pay for humans to go out and write a web scraper and then actually scrape it and then go through and determine the quality of that. And maybe there's some amount of compute that you're spending to kind of go through the data and filter it with various types of quality filters. So there's already some kind of computational cost to gathering and scraping this internet data set. That's also the case with synthetic data, right? And it's a little bit more direct because a lot of synthetic data generation is literally generated. So if you have to generate these rephrasings, you're paying for GPUs now, right? You're not just paying for a human who has to scrape it. The web scrapers don't necessarily need a GPU, right? They're just kind of like pinging a bunch of different things and scraping the information. But there is some cost to actually generating this data. So you have to kind of play with that as well, right? Where, hey, we're generating this, we have this data that allows us to train our model better, but if it costs money to generate that data, to that we then need to train on again, right? The more data you have, the more your training cost is. So there's kind of like a Pareto frontier, as they say here, right? Where, okay, there's multiple different things that you have to optimize, so you don't necessarily have an infinite budget to generate infinite data. Okay. Generator-driven paradigm, a tale of 2 approaches, 2 different types of main approaches for generating synthetic data here. Generator-driven and source rephrasing. And both of these are constrained to text, so this entire paper is constrained to text. But we'll kind of expand into a couple other modalities later to show how this could be applied broader. But the generator-driven paradigm is when you use large-scale models to generate training data from scratch, encapsulating the knowledge embedded within these models. And this one just feels like the most sketchy to me because you're really just at the mercy of the hallucination. So, for example, you could ask GPT-4 to create a blog post about dinosaurs, right? And what's happening there is that, okay, you have to, now all the information about dinosaurs in that generated blog post comes from the knowledge inside the model itself. So GPT-4 usually inside those multi-layer perceptrons, those FFNs, right? That's where the information is stored. So you're hoping that the dinosaur information in those FFNs is correct, and that whenever you actually generate this blog post about dinosaurs, there's no hallucinations in there that you're introducing, right? Which is easier and easier, or that assumption is better and better because these models are becoming less and less hallucination prone, but it's still not necessarily great for that reason. And it's also not great because this paradigm relies on using a powerful existing model, such as a knowledge bank, and is constrained by the high computational cost of accessing state-of-the-art generators like GPT-4, right? So if you have to, if the cost of generating that dinosaur blog keeps going up as we get GPT-5, GPT-6, then maybe this generator-driven paradigm, it becomes a little bit less enticing. And that's where the source rephrasing paradigm comes in. In source rephrasing, here's a variant of it they call web rephrase augmented pre-training. It's just another way of kind of saying this, where you're augmenting your pre-training, right? That idea of data augmentation by rephrasing the text. So this leverages existing web documents and employs smaller models to rephrase this content into higher quality, structured, and or targeted formats. So this is cheaper, right? Because rather than generating from some of the most expensive models out there, like in this case, it would be GPT-5 or Grok 4 or something like that, you're instead taking data that already exists and then rephrasing it with something much smaller, right? Something like a 3B model or an 8B model. So this is going to be cheaper to generate a lot of variance. And you could think of this is actually what happens in image augmentation as well, right? So whenever people use image augmentation for something like Dino, right? The recent Dino v3, there's for sure a bunch of image augmentation that's being used in that. The image augmentation that's used for models like Dino v3 isn't something super hardcore like a GPT-4, right? It's basically some hard-coded algorithm like a flip or a Gaussian blur filter or something like that, right? So it's like these hard-coded small algorithms that allow you to augment your data set. So this source rephrasing, yes, it's still a model, but it's a very tiny model. So this is kind of a little bit more close to the image augmentation, and because of the lower computational cost of doing this type of augmentation, although in this case, of course, this is text. Open Room XYZ. Generate books from 1 or 2 books, summarize books, write new books. Okay, something about summarizing. The error correction in data sets will become the key. Yeah, what does error correction really mean too, right? That's another kind of important question to be asking here. The rephrasing has become the dominant paradigm, with state-of-the-art LLMs like Kimi K2, Qwen 2.5, Grok, and GPT-5 reporting substantial use of and or meaningful gains from source rephrasing. So these guys maybe they have some connections to the OpenAI and XAI teams, but it seems to me like they were confident enough to put this, so it's potentially true, but they're basically saying that Grok 4 and GPT-5, which are basically the most advanced models that we have now, are making substantial and meaningful use of this source rephrasing. So this type of data augmentation with rephrasing seems to already be extensively used by the frontier labs, which we could have probably guessed, but it seems here like they're kind of almost confirming that. Okay. Introducing Beyond Web. Format transformation. Converting web content into question-answer pairs, style modifications, and content restructuring to improve information density and accessibility, right? So whenever now we're inside this rephrasing paradigm. Inside this rephrasing paradigm, there's actually a lot of kind of nuance and complexity, right? So how exactly are you rephrasing this, right? And here they start introducing different ways of doing that, right? So you can modify it, make it more, they call pedagogical here, but it's like basically making it easier to learn from, right? Just by changing, I guess, the words that you use, right? Even just going through and changing picking one word in every sentence and then changing that word to another word that's similar, right? There's so many different strategies that you could use here to do this type of text-based augmentation. Okay. But this paper, the way that it's organized is actually quite clever and quite good. It's basically they take you through these experiments that they did. So for each of these sections that we're going to go into, it's basically they're going to present the experiment and then they're going to present the results. So I actually really like this format, right? Because it allows you to it almost feels like you're part of the experimental process here, and you can ultimately draw your own conclusions from the data. They're just kind of presenting, hey, here's the experiment that we did, and then this is what we got. So this first experiment here is they're going to be just comparing synthetic data to non-synthetic data, right? So an internet scrape, and they're going to specifically choose this red pajama, right? Because it's a well-established baseline with minimal curation, blah, 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 okay? And they're going to compare it to some synthetic data sets. So specifically Cosmopedia, which is 27 billion tokens, Nemotron Synth, which is 1.5 trillion tokens. This is NVIDIA, which is also kind of generated by applying diverse rephrasing prompts to high-quality classifier selected input. So there's two things here. You have this classifier selected input, so there's a filtering, right? So there's some text-based classifier, right? So it receives some chunk of text, and then it says, okay, I classify this as either high quality, low quality, something. There's probably other different classes there, but they're filtering through it and then rephrasing it, done by NVIDIA. Kind of a similar thing here. Actually, Cosmopedia, this one seems generated. Stories generated by Mixtral using web-derived prompts covering a predefined set of topics. So this is more generator-driven paradigm. And then they have RAP, which is Red Pajama rephrased by Llama 3.18b. So just an 8b model rephrasing Red Pajama. Okay. I think they had a chart for that one, but I don't know why they don't put it there. All right, I think we'll get to the chart later then. Let's go here. Synthetic generation infrastructure. I thought this was interesting. They talk about the specific technologies and frameworks that they use. So they started with Slurm on an AWS Hyperpod of H100s. But the system was rigid, slow to iterate on, had deployment constraints, and made it difficult to track experiment choices. I don't really have experience with AWS Hyperpod, but I have experience with other AWS services, and generally it's kind of a huge pain. Slurm is popular in academia. I've seen various academic labs that use Slurm, but actually Ray and Kubernetes and VLLM, these seem... I've used Ray and I've used Kubernetes, and I think those are much more kind of modern. So it's interesting that they also kind of agree with this. Move to a solution using Ray and VLLM on Kubernetes, right? VLLM is for the inference, and then Ray is basically allows you to kind of create jobs and spin jobs, and then the jobs kind of all... So it's kind of like an orchestration framework, right? Where you can kind of control a bunch of computers and have basically something that abstracts away the compute to like the actual task that is being done. So you as the kind of experimenter can say, okay, I need like these 10 jobs done, and then I'm going to send it off, and then Ray's going to figure out how to kind of allocate that to different computers, which is kind of what Kubernetes does as well, right? But okay, evaluation setup. Multiple choice questions are then using a relative scoring method. So this is how they're going to determine the intelligence of the model. And you can see here, this is the actual results from that. Okay, so you have, again, Cosmopedia is the generated paradigm, Nemotron Synth is a rephrasing and filtering paradigm, and QA Wrap is also a rephrasing paradigm, and then RPJ is the baseline of just straight internet data. And you can see here how the rephrasing paradigm and the generative paradigm, these are kind of, they're not necessarily too different, right? And these are chosen to be different benchmarks. So like they want to show that with synthetic data generation, you're not necessarily just narrowing the model, right? A lot of people say that one of the critiques of synthetic data is that because the synthetic data that you generate is usually from a narrow distribution, if you train your model on that narrow distribution of synthetic data, even though your model performs better on benchmarks that are related to the distribution of the synthetic data, they lose some of their generalization capabilities. So that's why they chose kind of a very wide suite of benchmarks to show that, hey, we're training on this synthetic data, but we're still maintaining the generalization capability of the model, right? So it's not like we're kind of just pigeonholing it into one specific task. And you can see here that Beyond Web, I guess, beats all of them, right? That's why this is the first table, because they really want to show how strong their results are. And some of these, they do get relatively impressive bumps here, but note also how it's also dependent on the size here, right? So they tried at a couple different scales, and it seems to me like the difference is more pronounced in the smaller domain. Again, I mean, take with that whatever you want, right? So you can read into that in whatever direction you want to read into that. But a big part of the story here is that Beyond Web enables substantial computational savings during pre-training. So what they're trying to say here is that Beyond Web matches or exceeds Red Pajama's 120B token performance in just 23.2B tokens. So what are they trying to say there? What they're trying to say there is that ultimately there's this kind of relationship that has been established where, hey, if you have this size of a model, you can train it on this many tokens and you'll get this quality of an output, right? And this is where the whole chinchilla scaling law comes from, and they actually mention it later here. I think let's go to the actual conclusion here. Let's Control F chinchilla. Yeah, here we go. 50x beyond chinchilla optimal compute, right? Which is kind of like, I've been saying this for a while now, but like, to me, the chinchilla scaling law is basically bullshit. You know, like people just ran with it, but if you actually look at the original paper, it's just a very kind of narrow experiment on very specific model architectures on very specific sizes with very specific. So it's like people have tried to extrapolate this chinchilla optimal compute idea to pretty much everything, when really the applicability of that, I think, is much more narrow than people put it. And this paper kind of demonstrates that, where, hey, we're capable of training something to the level of another model of the same size that's been trained on a much larger amount of data, right? So Chinchilla tells you how much data how many tokens can you train a model with this specific size on, right? And here what they say is, hey, we got a model, an 8B model, that basically gets to the same place that you would get to if you fed it the 180B tokens of Red Pajama, but we just had to feed it 23.2B tokens. Right? So what that means is that not all data is the same, and there's some data that's significantly more information dense, or information dense is maybe not the right word, but it's significantly better at getting the model to learn something, right? And this isn't even necessarily, there's a very old paper by, let me see, Andrew Ng, mini data sets or something like that. I'm not going to find it. I've already forgot what the title is, but like there's like old papers where they, for example, took ImageNet and made this little tiny ImageNet, like pseudo ImageNet data set that you could train on that little tiny pseudo ImageNet data set and get something that was, almost as good as something that trained on all of ImageNet, right? So this idea of kind of like distilling a data set, right, which is overloading this term distillation, because distillation has kind of a different meaning, right? But the idea of taking large data sets and kind of curating them down into only the high quality stuff, or in this case, rephrasing it and then kind of almost compressing it such that you can reduce the pre-training. That's a very real effect. We keep seeing that time and time again, and I think there's something there, right? So moral of the story, if anybody tells you something about chinchilla, you can just be like, that's basically bullshit. There's nothing there. Saskia Ludden, Hype Hoopo, just cooing now. How's it going, Saskia? Performance gains are not constrained just a few standout benchmarks, but are broadly distributed, reflecting the generalizability enabled by high-quality, diverse synthetic data. Right? So your synthetic data not all synthetic data is the same. You can have high-quality synthetic data, and you also want to make sure that it's diverse synthetic data. Okay. Systematically evaluating synthetic data. Modern pre-training budgets are beginning to exceed the scale of high-quality web data, which means we're basically running out of data. There's this data wall. The top 3 most common styles of web data are personal blogs, product pages, and news articles, whereas deployed models predominantly interact in conversational or instruction formats. So what they're trying to kind of bring attention to here is that ultimately we are using these models in a chatbot capacity, but a huge amount of their pre-training is not in that chat format. So maybe there's something to this idea of kind of style matching, right? Where, hey, maybe we should take all of the pre-training data that we use and rephrase it into this chat format, and maybe we could get to the end of pre-training much faster because we can effectively condense our data set down because now the model's already in that chat format, right? Let's keep going. Here's an experiment. Okay. Research question 1. So this is the experiments that I was talking about. Are generator-driven approaches approximated by summarization, restructuring and distilling existing knowledge into more compact and informative representations? And actually, like, so whenever they say distilling existing knowledge into more compact and informative representations, that actually has a lot of parallels to model distillation, right? Whenever people distill models, usually what they're talking about is taking a larger teacher model and then training a smaller student model to effectively match the teacher model. But the way that matching is done is usually you try to match some of the kind of, not the actual tokens, but the like representations that exist in that teacher model. Maybe the last layer, right? That last layer is basically just this high level, but extremely compact and informative representation of what the input was to that big model. So whenever you do this type of model distillation, you're not trying to get the small model just to match the output tokens, right? Because that's a very kind of a sparse signal. You want it to match something much more dense. So even within the distillation that we're all familiar with, right, this big model to small model distillation, you already have this exact same concept of, hey, we want the most compact and informative representations to serve as the loss function and then the gradient that goes into the small model. So there's kind of the same thing here where, hey, can we take this data set and distill it into still sequences of tokens, but sequences of tokens that are more compact and informative in terms of kind of like the just semantic juice that's inside of them. Question from Open Room. Would you say that non-GPU rich person can speed up AGI development by creating data sets and publishing them on Hugging Face? Yeah, actually, that's a pretty good way to do it. I think if you have some kind of niche knowledge and, right, like let's say you're an expert on insects, right? Like if you put all your insect knowledge and start creating kind of very high level insect data sets and then filter a bunch of existing insect data out there, I think that is a way to increase the speed at which we reach AGI and ASI. I would say we already have AGI. You know, I've been pretty clear about that I feel like AGI was ChatGPT, but we can get faster to ASI by just getting experts to take all the knowledge that's in their head and put it into a data set that models can train on. Okay. Consider 2 approaches. Cosmopedia, which prompts a large model to explain or teach concepts, reorganize knowledge into compact, pedagogically optimized outputs. Okay, so Cosmopedia is rephrasing. And then summarization, which compresses existing text using a prompt that aims to preserve essential information while reducing length. Okay, so what we're comparing here is basically within this rephrasing paradigm, you have rephrasing that's kind of tends toward compression, and that's what this summarization is hey, can you get a small model to effectively create a new sequence of tokens which has the same knowledge as the original seed data but is lower in length, right? So kind of like a black box compression. Cosmopedia is not really trying to compress, it's more trying to just organize and optimize the output. Say, hey, rephrase this stuff slightly differently, but you're not necessarily trying to compress it by half, right? And what they find here is that simple summaries match generator-driven methods. The summarization approach nearly matches the performance of the more sophisticated and compute-intensive Cosmopedia approach. And here's the actual plot. So average accuracy here, so higher is better. So this is a smarter model than this. And then token seen billion in the bottom here, this is basically how much compute you've put into training, right? So here, the model has only been pre-trained for a small amount of time, and then here the model has been pre-trained for a longer amount of time, right? And you can see RPJ, the Red Pajama, HQ. HQ is like a high-quality subset of the Red Pajama, I think. That serves as the baseline, right? So you literally see the definition of baseline here. Baseline, right, literally comes from the fact that it's the line that forms the base. So in a plot, it's the line that's in the base. So it's a good baseline because it's the bottom line, right? I love how you can kind of etymology that. But you can see here, summary versus Cosmopedia, slight edge here to the Cosmopedia. But the fact that it's about the same shows us something, right? It demonstrates that even naive summarization achieves substantial improvements similar to those of Cosmopedia. Okay, so even just taking a 3B model, or even using, in this case, an 8B model and summarizing, so going through Red Pajama and saying, hey, here's a blog post about dinosaurs, turn it into a paragraph about dinosaurs. Even if you use a relatively dumb model to do that and then train on the outputs of that, that's going to actually get you something, right? Beyond substantial gains, possible beyond basic distillation. Okay. RQ2. Can synthetic data break the data wall? Okay. Second type of experiment. Can synthetic data effectively compensate for limited high-quality real-world data? Explores whether there exists a fundamental limit to the model performance that cannot be overcome through synthetic data. Okay. Illustration of data splitting and corpus construction strategies. Full data 2x repeat continuation. Let's go here. All of these perform about the same. Performance comparisons with different data augmentation strategies. Dark blue line represents beyond. They always have this one here just because, right? The Beyond Web is basically their mix of different synthetic data generation techniques. So it's almost like a mix of the different approaches. And all of these plots, and there's a bunch of these plots here in these experiments, they always have this Beyond Web at the top. And the Beyond Web basically represents kind of like a superset of all the different synthetic data techniques that they use there, that they mention here. So basically every single one of these plots is like the combination of all the approaches and then like kind of almost narrow version. So it's almost like a ablation kind of experiments if you want to think of them that way. Okay. Simple continuation provides limited improvement over repetition and may not be able to breach the data wall. Synthetic data must be well designed. So what they're saying here is that continuation is kind of within the generative paradigm, where they're basically just taking, here's the first half of a random Wikipedia article, and then we want you to basically just continue that Wikipedia article, right? So it has all the kind of problems of the potential hallucinations, limited to the intelligence of the base model or the model that you're using to do this continuation. It's expensive because the model that you're using for that continuation is potentially larger, just so it's not super hallucination prone. But that type of continuation kind of barely beats, or it's about the same as full data and barely beats the 2x repeat. The 2x repeat is basically just like you take a small amount of the data and then just do multiple epochs through that data, right? Which is kind of what we do. And general, right? You're generally, for large pre-training runs, I don't think they do very many epochs, but for most of machine learning, you know, especially other types of modalities, you see a lot of epochs. So 2x repeat is basically just go twice through that data. But you can see here, there really isn't that much of a difference here. It starts to become more pronounced as you have more data or your pre-training budget gets higher, right? So as your model has seen more and more data repeating the same data, you kind of don't get as much juice as the full data. But the continuation doesn't give you any more, which is important. Message retracted. What's going on, Open Room? I got this feeling that we should prune memorization out of the LLM by giving them so much data that generalization is the only way for the loss to go down. Yeah, I mean, that's kind of, we're already in that paradigm, right? I think that's already what's happening, right? So whenever you look at what's going on with the models that we have now, right? You look at the training tokens that go into the models, and you look at the model capacity, and there's a huge difference there, right? So the magic of machine learning is that these neural networks and all the kind of related architectures can pretty much learn any function, right? They're these function approximators that can learn any function, but the data that you're giving them is so much bigger than the capacity of the model that the model has no choice but to learn some kind of generalizable, lower level kind of knowledge rather than actually memorizing every single thing, right? So already we're forcing the model to not overfit by making the data set size relative to the model size huge. So we're already in that paradigm of like, hey, we figured out that if you make the data sets like absolutely massive compared to the model's not going to be able to memorize every single data point, and it's going to instead create this weird kind of little AGI kernel, right? If you want to think, it's like, what is that, right? Why is that the case, that if we take the entire internet and try to compress it into this little neural net that's smaller than the entire internet, why does that result in something that has like almost like this human ephemeral quality to it, right? Nobody has answered that question. It's kind of magic, but we're already doing that. So now what we're trying to answer with this paper is, could you do that with entirely synthetic data, right? And what does it mean to design synthetic data that results in a model that is capable of generalizing to a bunch of different things, right? It starts to get pretty weird. The synthetic data must be well designed. Here's another experiment. How important is the quality of the seed data? So the seed data here refers to the actual data that you scraped, and then you're rephrasing that original seed data, right? So there's still kind of a fundamental limitation here, right? And the limitation here that they're kind of leaning into with this seed data is that, as they mentioned before, right, the quality of the data needs to be high and the diversity of the data needs to be high. So how do you get high diversity? Well, you can leverage the diversity of the existing internet data set, right? So like this whole rephrasing with seed data paradigm is basically saying, hey, let's start with random chunks of sentences or random chunks of our pre-training data, which is very, very diverse because it's the entire internet, and then we're going to basically rephrase that, which means that our rephrased synthetic data set has kind of the same variance or diversity as the original internet data set, which is probably the highest diversity data set we've ever created as a collective humanity. Right. So in this one, they do some comparisons across different quality combinations. So HQ refers to high quality, LQ refers to low quality. So obviously you have your baseline at the bottom, low quality web plus high quality web. At the top, you have, again, Beyond Web, which is kind of like the combination of all the approaches. That serves as the kind of top line. And then now what you're really comparing here is basically low-quality synth and high-quality synth, right? So that's these two lines right here. So this is interesting, right? Low-quality web plus high-quality web is significantly lower than low-quality synth plus high-quality web, right? But then high-quality synth and high-quality web is kind of about the same as low-quality synth and high-quality web. So what does that tell you, right? These results indicate that improving the quality of the input data for rephrasing improves the rephrased data even when there is overlap with the original input data. But improved input quality is not adequate enough for producing the highest quality synthetic data. Okay. So basically, if you have HQ web, right, even if you rephrase that in a low-quality way versus a high-quality way, the quality of the seed matters, right? So because you're depending on your seed data for ultimately the diversity, which is one of the most important parts of the quality, right? The quality can be like the actual like, is there trash in there? But it can also mean just kind of how evenly does your data set sample all the true data set distribution, right? So this kind of idea of like variance or diversity. And if you're relying on HQ Web for your seed data, then that HQ Web quality is going to matter. That HQ Web diversity is going to matter. And no amount of kind of like synth, high quality or low quality synth rephrasing is going to necessarily have a huge impact. So if you're using high quality source material, is crucial. How are people doing? People doing okay? Translating from one language to another language and back would probably be great as well. That's actually a very, very good point, OpenRoom XYZ. Maybe we use that to do a little bit of a side quest. So let's go on this side quest here. Let's go on to this paper here. It's called Dupo. People posted it on the Discord because it sounds kind of like Hoopo, right? Which is the name of this channel. But this is very kind of similar to what we're talking about here, right? So the main kind of course for today was this Beyond Web paper where we're talking about scaling synthetic data, right? This idea of kind of rephrasing internet scraped data for better pre-training. And this is a similar idea in which they make it sound very complicated. It's like it sounds like 10 times more complicated than it needs to be, but it's effectively kind of the same idea. It's like kind of like data augmentation of text data, right? So I think the best way to understand this paper is, for example, this figure right here, Dupo on mathematical reasoning. So here they call it primal task, but primal task is effectively the same as seed data, right? So it's like there's some original task that comes from some kind of math textbook, and then we're going to create a dual task 1 and dual task 2. So basically what these are is kind of like two different rephrasings of this primal task. So this is the task that you know that has the correct answer that some human designed, right? So you know it's all correct. That's a very, very good high quality seed data point, or in the terminology of this Dupo paper, it's a very high quality primal task. Now, what you want to do is figure out a way to create more synthetic data from this. And in this case, the synthetic data is effectively rephrased versions of that called dual task 1 and dual task 2. And yeah, basically that's this paper, right? This entire paper is just that. But they kind of like use all kind of intense kind of like math framing and terminology here to make it seem very, very hardcore, but it's actually a relatively simple concept. Like look at how unnecessarily complicated this is. A dual learning-based preference optimization framework that generates annotation-free feedback via a generalized duality. Like what? Decomposes a primal task's input into known and unknown components, then constructs its dual task to reconstruct the unknown part using the primal output and known information, e.g. reversing math solutions to recover hidden variables, broadening applicability to non-invertible tasks. Okay, so what do they mean here by broadening applicability to non-invertible tasks? So what they're talking about is that something that people have done a lot is exactly what you're talking about, OpenRoom XYZ, which is this multilingual translation where basically people will say, okay, well, if you have a data set that is basically here's the chunk of English and then here's the chunk of Chinese, right? You could basically flip that. You can now say, okay, well, here's the chunk of Chinese and then here's the chunk of English, right? So from that one data point, you now have two data points, right? Which is the same kind of data augmentation idea of just flipping the image, right? You have a picture of a cat. If you flip that cat image by 180 degrees, it's still a picture of a cat. So now from that one picture of a cat, now you have two pictures of a cat, right? So you basically duplicated your data set. And this is kind of the same thing, but in math, right? And you could do the same thing in translation, right? So it all boils down to these kind of clever data augmentation techniques that come from understanding the way that information in a specific type of text is has some kind of symmetry, right? So in language translation, there's this kind of natural symmetry of like if you go from A to B, you can also go from B to A. And this Dupo paper is basically the same thing in math, where it's like, hey, in math problems, you can kind of figure out like, okay, this is the unknown part, this is the known part, and then you can effectively rephrase that to create multiple math problems that are guaranteed to be as correct as the original math one, right? So it's all just data augmentation techniques. 87GN, you're in the chat. Welcome to the real world. I think that's a Matrix quote, right? Whenever he first goes in and then he comes out inside that like spaceship and he like pulls out the little plug and they're like, holy shit, dude, you've been in the Matrix this whole time. I hope the diffusion LLMs keep scaling well. They were a nice off-ramp for synthetic data. Yeah, very good point, Josh, right? 2 weeks ago, we did a stream on kind of diffusion models and autoregressive, and that was a big part of that story there, where, hey, diffusion models, because they kind of start from noise and then diffuse out the paragraph, right? There's this kind of inherent data augmentation there, right? Where basically each token comes from noise, and the way that you come from noise is kind of random, right? So like basically, if you were diffusing out this paragraph using a diffusion language model, right, sometimes this word would kind of appear before this word, and this word here would appear before that word, right? So like basically every time you diffuse it, because you're starting from noise, you're effectively kind of creating a new data point. So diffusion models have a natural kind of built-in data augmentation just from the task itself, right? So once you start recognizing this kind of idea of data augmentation, like a lot of these papers, right, you realize that that's basically what it is, right? This paper is just data augmentation. This paper is just data augmentation. It's just there's a million different ways of augmenting data, and if you can come up with a clever data augmentation strategy for some specific type of data, there's a lot of benefit to be found in that. Okay, the funny thing to do is to change the meaning of words in the middle of text. Yeah, that could be something. What up, Beast by Steak? How's it going, sir? Okay, let's go to the next experiment here. Is distribution style matching important? Okay, so this goes back to the, hey, conversation dialogue comprises less than 2.7% of internet text, yet the dominant use case for modern language lies in chat-based applications. So what if we just took all of our pre-training data and just turned it into conversations? Could we do pre-training faster and get to the end of pre-training faster, right? And actually, like, there's something strange about this. So if you've ever read kind of very old books, there's like kind of a specific type of very old book. I think there's a couple books by like Greek philosophers, and there's also, I remember this is the most random one, but there's like a miner manual. It's like a book on mining written in like the 1800s, and it basically explains how to mine, right? Like old school mining, where you basically like dig a pit, and like the way that it's written is as a conversation between a father and the son. Right, so this is a book on mining, and the book, you read it, and it's like the father's like, make sure you dig every 5 feet before you put a beam overhead, and then if you run into this kind of thing, do this. And then the son asks like, what if I do this? And then the father's like, well, then do that, right? So we already have a historical precedent of this, of passing knowledge or learning by reading information that is in a dialogue format, right? I don't want to mess this up because I know that people are really picky about this, but there's like a specific Plato book that I read where it's like a conversation like this as well, where it's like this, it's not even a real conversation, where it's like a fake conversation. And the reason that it's portrayed as a fake conversation is so that there's someone who's kind of asking for knowledge and then someone who's giving the knowledge, right? So there's already something rare, right? Humanity has already figured out that rephrasing things into these dialogues could be a way of turning material into more effective learning material, which I think is interesting. Okay, so let's actually go into this experiment though, because these guys did an experiment on it. So they try varying conversational ratios, 10, 20, and 50%. So again, they're basically using Red Pajama only, maintaining a 20 billion token training budget, right? Trying to keep all the different variables the same so that they can say, okay, if we increase the ratio of conversation data, what improvement in final accuracy do we get? And this looks a lot more impressive than it is, right? So obviously you're like, holy shit, wait a second, 50% conversation data, we get much higher. It's like, okay, whoa. Look at the y-axis. We're talking about 43.2 versus 44. So it doesn't seem to have a huge difference, but there is something there. There is a kernel of truth in this idea that like, hey, style matching to conversation style could actually improve the quality of that data. So, yeah, Socratic dialogues, is that what it is? Yeah, I mean, I'm just like I'm kind of a noob when it comes to kind of like old school philosophy and like Greek writing like that. And I know that people like are way deep into that, you know, like they basically just they know all the people and all the books and all the different things. So I didn't want to say something incorrect and then get absolutely murdered in the comments for getting it incorrect. I just wanted to mention that I've seen it before, right? Let me see if I can actually find that. Like 1800s mining manual, father, son. I'm never going to fucking find this, but it was like a book that was literally like the way it was written was just so weird. All right. I'm never going to find that. I won't even try. Okay, let's keep going here. How important is diversity at scale? How important is diversity in synthetic data generation? Training dynamics across model scales showing performance improvements relative to Red Pajama baseline. So again, our baseline is Red Pajama. Beyond Web, Cosmopedia, Nematron Synth, and then here they're trying 1B, 3B, and 8B. I don't know, there really doesn't seem to be a huge difference here, right? Like the trend is kind of about the same. Cosmopedia and QA Wrap. Cosmopedia is the generative paradigm. QA Wrap turns it into question answer. So kind of like the conversational, and then Nematron Synth is the filtering and rephrasing. So filter rephrase works slightly better than Cosmopedia QA Wrap, but then Beyond Web, which is all of them together, beats all across all scales. So really what they're trying to show in this experiment is that this isn't something specific to one scale of model, but similar to the chinchilla, the critique that I have on the chinchilla, this is a very narrow experiment, right? So they're like, oh, we're trying different scales. It's like, okay, you tried 1B, 3B, and 8B. Okay, what about 70B? What about 600B? What about 270M, right? So like, again, you cannot extrapolate too much beyond the experiment. So be very careful about that. So it could be the case that if you try this at 70B, the green line is higher than the blue line. You don't actually know. Diversity leads sustained improvements. Diverse generation strategies continue providing learning benefits throughout extended training, even in overtrained regimes. Overtrained regime would be whenever you basically, the model has gotten so many epochs over your data set, which basically means that the size of the model, right, the model capacity is one variable. Then there's the size of the data set, and then there's how many times you go through that data set. So overtrained means that you've gone through that data set too many times. You've basically too many epochs. The model has seen the data points so many times that it's gotten closer to basically overfitting or memorizing that data. But if you are doing diverse generation strategies, which again is just kind of a different way of saying, hey, we have a data augmentation that is very varied, lots of different types of data augmentation, then we're capable of training our model for more epochs, which again, it feels very obvious to anybody that's trained image models, right? Where it's like, hey, if you're just doing left and right flipping, you're not going to be able to train for as many epochs as if you do left, right flipping and rotation and blurring and skewing and kind of affine transform. So the more diverse your data augmentation strategies are, the less susceptible to overfitting and overtraining you are going to be. And then this is basically that same intuition, but in the modality of text. How's it going, Julien and Max? Saskia. Hoopo is a legend. We know you are under a lot of pressure with the nerd army watching. I mean, I don't, like I've just accepted that, like I have some credentials, I've worked at some impressive places. I do have like academic credentials, but I'm definitely not like a super intelligent. I've been in a lot of rooms with a lot of people that are way smarter than me. So I know I'm not necessarily going to get everything right. I know I'm going to say things that are incorrect. I cringe about all the things that I said that are incorrect, but I know there's even more things that I don't even realize are incorrect, right? So there's probably things that I've said that I think are correct, but I don't even realize that they're incorrect. And, I think you just got to live with that, You just got to be okay with the fact that sometimes you're going to look like an idiot, and that's the only way to get better at things. So I would say I'm definitely more knowledgeable now than I was a year ago, and I'm more knowledgeable a year ago than I was 2 years ago, right? And then you can keep improving. And there's going to be people out there that are way more knowledgeable than you, right? But if they're kind of punching down, if they're using their position of super high math knowledge to just talk shit on the people that don't have as much math knowledge, then you don't really care about their opinion anyway, because they're kind of an asshole. Oh shit, Josh Phillip found it. A Conversation on Minds. Yeah, here we go. Is it just a book? Conversation on Minds PDF. Yeah, here it is, dude. I'm so glad you found that, Josh. That's crazy. Yeah, look at this. As you have been in the mines, Father, blah, blah, blah. Very good, Father. Have you experienced the effect of these gases? Some people say they have a choking nature, Father. I have often been affected by these gases and have yet to be brought home. So it's like, why did they do this, right? It's such a weird way of like having a textbook. Like imagine a math textbook that was phrased in this type of way as well. But maybe this is a better way of doing it, right? Like think about education and where education goes. And we already have kind of this idea that educating with chatbots, right? There's this famous kind of Alpha School, I think it's called. It's basically a new type of like school that people are starting here in Austin, where it's basically like it prioritizes putting you in front of a chatbot. So a kid is learning math from a chatbot. And if you're learning math from a chatbot, it kind of is like this, right? It'd be like student. Replace the word son with student and replace the word father with chatbot. So it's like son. What should I do after I do this? Chatbot. After you do that, you should do this, right? So it's like, maybe that's the better way of learning, right? Maybe this kind of like teacher-student kind of explicitly in the form of a conversation is the best way to learn something. Okay, let's keep going here. Multifaceted approaches continue providing valuable learning signals throughout training, whereas single strategy methods saturate. So aka don't just use one data augmentation strategy, use multiple, or if you're going to be generating synthetic data via rephrasing, different types of rephrasing, use different types of rephrasing. While a rephraser spans a 7-point range in general accuracy, the quality of the resulting synthetic datasets is strikingly similar, differing by less than 1 percentage point across generators. So there's a lack of positive correlation between the model's general language modeling ability and the synthetic data quality, highlighting that even comparatively weaker models can be highly effective rephrasers. This is the one part that I kind of disagree with, where They say, okay, we wanted to test whether you change the intelligence of the rephraser model, basically the model that's generating the actual synthetic data given a piece of original seed data. And if you have a 5414B and compare it to an Olmo 27B, right, intuitively, the 5414B is twice the size. It should be able to rephrase better, and therefore the synthetic data that you generate from it should be better. But that's not what you see, right? You actually see that Olmo 27B is higher up here on this accuracy, which means it's generating higher quality or better synthetic data. But the reason I don't trust this result is because it's like, these are all kind of the same to me, right? They're making a big deal that the 5414B is twice the size of the Olmo 27B, but to me, it's like all these models are kind of about the same. It's like Olmo 27B, Llama 3.18B, Mistral 7B, and 5414. Those are all the same to me, right? I feel like if this result, if they would have shown it with like the 600B DeepSeek model and then like a 1B or the 270M Gemma model, then that would have been powerful, right? If you really go from the full continuum of models, right, from the tiniest little tiny dumb model to the biggest massive model, if you still see this relationship, that would have been crazy. But I bet you it's probably not the case. I bet you if you put the DeepSeek 700B model, it would be like up here, and then if you put a really really tiny model, it would be down here. Right, so I do think there probably is some effect where the bigger the model, the more intelligent the model, the more capable it is at rephrasing or augmenting your text data set. And this is the same thing with the size. So they try a couple different sizes of rephrasers. So Llama 1B, 3B, 8B. Here you go. Here's the exact kind of plot that I'm saying. So there is a little bit of that relationship there. Right? But larger generators consistently produce better synthetic data. But here's what I'm thinking about. Okay, if there is some separation between the size of the model and the quality that it produces of synthetic data, that means that this is you can hill climb this, right? If you can hill climb this, right? Climb the hill using reinforcement learning, right? Basically some kind of iterative way of improving the score on this. That means you can actually start creating models that are ASI and rephrasing or superhuman teachers, right? And then the interesting question is, if you create a model via reinforcement learning that is superhuman or extremely good at rephrasing and creating synthetic data for language models to pre-train on, is there transfer between that task and the task of teaching humans? And I think there probably is. I think it's probably the case that if you use reinforcement learning to make a model that's extremely good at rephrasing data so that it's better to train on or pre-training, it probably also works for math. So what does it look like when you take that superhuman rephraser synthetic data creation model and then get it to try to teach you math? What does that look like, right? What does it look like to basically condense an entire, condense calculus into one page of text, right? Or condense all of history into one page of text? Is that even possible? I don't know. I feel like it could be, right? So I can't wait to kind of live in that future where there's these kind of superhuman kind of condenser summarizer kind of teacher models that know the exact way of phrasing things so that it's optimal for learning. Okay. Let's keep going. Let's look at some of these other papers. So that's basically the end of this paper. But, let's also explore some of these other papers that have themes that are kind of similar to the synthetic data theme we just went. So Here's NVIDIA Nemotron Nano 2, a hybrid Mamba transformer reasoning model. So basically this is a little 9B model that has this kind of hybrid architecture that we've seen before, right? So there was like a point last year where we read a bunch of Mamba papers. It seemed like they was going to take off. And then we read this paper, I think it was called Jamba, where basically they mixed in. So rather than having just attention or just pure Mamba or pure attention, they kind of weave in these attention blocks with these Mamba blocks. And it ended up performing better than either pure attention or pure Mamba. So it seems to me like now that the kind of idea has been explored more, it seems like this is where Mambas are going to end up, right? So these type of Mamba models, we're not going to see pure Mamba models. What we're going to see is these kind of hybrid models. So that at least gives us closure there. But the important thing that I wanted to point out in this paper is that this Nemotron Nano 2 is pre-trained on a large corpus of high-quality curated and synthetically generated data. So we're already seeing this happening, right? Where pre-training is no longer happening on internet scale scraped data sets. It's now happening on these pre-trained, curated synthetic data sets, right? So, for example, they generate synthetic data for STEM subjects, including astronomy, biology, chemistry, math, and physics. You have question generation, so they're using these Qwen 330B, Qwen 3235B, and DeepSeek models to basically rephrase. You can see here, create a new question that explores similar concepts but offers a fresh challenge, create a new question that requires more logical steps or involves more advanced concepts. These are kind of generative paradigms, so you're kind of hoping that the question that the model generates is kind of valid, so it's a little bit less rephrasy, more kind of pure generative. Create a new question that differs in type from the original question. We also regenerated the Nemotron Mind dataset, a math-informed synthetic pre-training corpus. We applied 7 prompt templates, so again, kind of using the best practices from this as well, right, where they're saying, hey, the more varied, the more different types of rephrasing or kind of synthetic data augmentation in text modality that you can use, the better. So what does that mean? That means perhaps using different prompt templates, right? So you can have rephrase this question in a teacher-student, rephrase this question as an interview, rephrase this question as a debate, right? So like each one of those is going to produce a slightly different rephrasing, which means it's a kind of like a different type of data augmentation. Consistent improvements across math, reasoning, and general knowledge. So again, that's agreeing with the trends that we found in the earlier paper. Prompting an LLM to generate questions based on short snippets from our curated source code. So again, same kind of idea. You start from seed data, or as they call it here, primal task, right? So you're relying on existing diversity within the seed or primal data set in order to generate a high diversity synthetic data set, right? In this case, they have some curated source code, and then they basically generate more coding data from that. This one was a little bit more complicated, but I thought it was interesting to highlight it here. They gather all the documents in undergraduate and graduate level math, chemistry, biology, physics, and medicine. Then they chunk each document into snippets and embed them with a large E5 large model. So basically they're doing RAG here, right? They're basically saying, okay, we're going to take all this information, we're going to create little embedding vectors for every 512 token chunks. Then we're going to query this giant database that's indexed by these embedding vectors and find the nearest neighbor text snippets to each query documents. And then these snippets function as our seed context that we then pass into Qwen 2.5 72B instruct model to generate multiple choice and free response style QA pairs based on the information contained in the snippet. So this is almost like RAG for synthetic data generation. So again, another clever kind of little trick here, right? So it seems like there's so much alpha in coming up with slightly clever ways of generating synthetic data, often using kind of relatively complicated pipelines that involve potentially different models, right? Which again is a recurring theme in all of these streams. It seems like every single week, the papers that we read have this type of pattern in it, right? This type of framework where you're using multiple different models to curate and filter and generate and tag and label and increase the caption and like all these different things to basically take your data set and augment it. Question by Saskia, what about biases? There is going to be biases that are introduced in this, right? So like if you're using one specific model, such as the Qwen 2.5 72B Instruct to do all this type of rephrasing, then whatever biases exist in that are going to then perpetuate. So the answer to that, right, is as we saw here, right, they keep showing you in all these charts that kind of a diversity of synthetic data generation approaches performs better than kind of any one specific approach. So I think you could apply the same thing to rephrasing models, where I bet you a combination of different models is going to be better than one individual model, right? So an ensemble of rephrasers is better than a single rephraser. And the reason that's better is because each individual rephraser is going to have slightly different biases. So by ensembling together all of them and using all of them, you kind of, the biases kind of, I don't want to say cancel out, but like they kind of aren't as pronounced. Diversification is key. Yep. Okay. I thought this chart was interesting. So this is again from the NVIDIA Nemotron Nano 2 paper, but specifically this here. So this is the data mixture. They have some kind of 3-phase training, right? You can see pre-training, then I guess people are calling this mid-training now, and then fine-tuning at the end. But look at this. Syncrawl high versus crawl high. So I think this is web crawl data filtered for high quality. And this is web crawled data filtered for high quality and then synthetically rephrased. And you can actually see that there's more of this than there is this. So I thought that was kind of interesting. There's more synthetic crawl data in the Nemotron pre-training corpus than there is original crawl data. Right? I would have thought this mix would have been flipped. I thought that you would have probably had maybe 20% crawl high, maybe 10% synthetic crawl high, but it's actually it's like flipped. So we're already training on more synthetic data than normal data, right? It's not just, hey, here's a little bit of synthetic data. It's like, no, like the majority of this is already synthetic data. Okay. Here's another paper. Time, thinking beyond images. Perform diverse image manipulations and simultaneously enhance logical reasoning capabilities through code. So this is, if you remember what, I think it was GPT-4o, or maybe it was o3, but one of the GPT releases where the demo they had where it was basically a picture and then it would like zoom into the picture. So you would ask it like this. This picture shows a typical American country style residence. On the right side of the picture, there's a stool. What color is the stool? So if you asked a vision language model this just generically, right, it would take this entire image, turn it into patches, then embed those patches, feed those patches into the actual language model, and the language model would have to answer the question based on a lot of kind of irrelevant information, right? It's going to have to answer the question of what color is the stool, and then, but think about all the tokens in the context. All the tokens in the context just are like green grass, green grass, green grass, blue sky, blue sky, blue sky, house, 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 house. So it's like, most of those visual tokens are like not actually giving you the information that you want. So someone at OpenAI came up with this kind of clever idea of like, hey, why don't we give the model a tool? And that tool is the ability to kind of crop on a specific part of the image, right? So iteratively crop and rotate and potentially zoom in on specific parts of the image in order to answer the question, right? And they call this visual reasoning. So in order to do this type of visual reasoning, right, there really isn't a data set to do that, right? So how are you going to do that? Well, you're going to effectively synthetically create that data, right? You're going to manually construct this time data. You're going to deliberately create a constructed data set that basically does this cropping, right? So you know where the thing is, and then you're going to basically because you know where that thing is, you can basically crop to it directly and then use that as a data point for training your model how to crop into parts of the image and then get the specific information. Let me quickly blow my nose here. So here's synthetic data generation being used for teaching a model how to use a kind of specific suite of tools for this type of visual reasoning. And it's really not that much either, right? So if you look at the amount, they have it for multiple tools here: rotation, cropping, low contrast enhancement. But you can see here 14K samples, 28K samples, 10K samples, 15K samples. So really not huge data sets. So you can generate a relatively small synthetic data set that will teach your model how to use a specific suite of tools, right? And right now, these are kind of being manually created. So there's some human that's coming up with a specific code that creates this synthetic data. But I think we're not far away from models that do it, right? So some kind of language model that has been trained through reinforcement learning to create synthetic data sets that are optimal for teaching a model how to use a specific suite of tools, right? So models that can teach models how to do things, right? And that has so many implications for so many different things, including like robotics, right? Imagine a model that basically designs robotic simulations and robotic synthetic data sets to more efficiently teach a robotics foundation model. Here's the conversational data set. Manually construct multi-round conversational data sets aimed at teaching the model to leverage historical code execution outcomes for a deeper analysis and error rectification. Here's an interesting one: error correction. So a synthetic data set where they make the model synthetically fuck up and then correct its own mistake. Right? So you know that, I don't know if they call it the eureka moment or something like that, but there's like some moment in the DeepSeek R1 where through reinforcement learning, the model accidentally discovers the ability to kind of correct its previous thing, right? So it's like halfway through the reasoning chain, it goes like, wait a second, what if I did this? And then it goes down a slightly different path. And that wasn't taught explicitly to the model. It wasn't part of the training distribution. It's something that the model kind of discovered via reinforcement learning, right? That's one way of kind of getting the model to learn how to correct itself, but that's a very sample inefficient way because you basically have to hope that the kind of randomness of reinforcement learning exploration eventually leads to these error correction moments. A much better way of getting the model to kind of have this error correction behavior built in is to create a synthetic data set of error correction moments and then train the model on that. And in fact, once you do that, you're probably more likely to run into error correction reasoning traces when you do the RL. So in this way, you're kind of bootstrapping this ability in the model, right? So, and this applies to the tool use as well, right? So like trying to get a model to get really good at a specific suite of tools using purely reinforcement learning when the model's never done those tools before is probably nowhere near as sample efficient as creating a small synthetic data set that first kind of teaches the model how to use those tools and then doing reinforcement learning on top of that, right? So this kind of like RL should really just kind of be the last final step here rather than necessarily doing RL to learn from scratch. So I know that that's a contentious subject. You know, some people think that RL from scratch is kind of the only way to do it, and they're kind of like bitter lesson pilled, as they call it. And then other people are kind of more like, okay, no, the RL is just at the very end, and really you just kind of have this curriculum of kind of synthetic data sets that leads you to like 99% of the way there, and then the RL just kind of corrects that last little bit. But we still don't know which one of those two is going to work. What's the current progress on the VLM on interpreting the image calibrated on X and Y axis? I don't exactly know what you mean by that. I would say VLMs are I don't know if there's necessarily super new stuff happening with VLMs. You know, I think if anything, there was like a moment where multimodal was very hot and people were like, you know, this is kind of when all the different companies were racing to kind of introduce kind of the VLM functionality to the AI products. But now it seems like everybody's moving into this kind of like reinforcement learning and code execute. So it's like they've kind of moved to coding agents, whereas so it feels like kind of VLMs are kind of like a little bit ignored, but they're still kind of steady improvement. All the VLM stuff right now is about long context video interpretation. Yeah. So VLM stuff is maybe more about videos rather than images, and everybody's kind of assuming the image stuff is kind of solved. Any new stuff paper on RL for computer use? Not off the top of my head, but yeah, there's for sure lots of different people working on RL for computer use. There's people at least in all the frontier labs, there's someone working on reinforcement learning for computer use agents. I can almost guarantee that. Okay. I think we talked about this one already. I've talked so many robotics papers at this point that I almost didn't want to include this just because it's like I feel like I'm kind of becoming a robotics paper streamer. So I wanted to stay a little bit away, kind of do something that's not robotics this week. But this paper did come out and it did use synthetic data, so I figured I might as well mention it. But here you have automated data generation pipeline for creating relation-aware placement regions, 33K samples, where you have this kind of process where first you extract the final position of the object, then you calculate the precise placement of the object, and then you render the spatial arrangement back into the initial image using Isaac GIM, which, by the way, they just released kind of a big one. So I saw this Isaac Lab and GIM. Yeah, they recently just pushed a bunch of crap here. So you can see here version 5.0 and then Isaac Sim also version 5.0. So seems like they're consolidating. But also, I don't know where this goes. You know, because really when I look at like Genie 3, like maybe the whole sim stack is fucked. You know, like there's this entire kind of what I call like legacy simulation stack, which is basically like meshes and Unity and Unreal and entity component systems and all these like this very kind of complicated way of creating simulations that we've been building for decades, right? But it's kind of complicated. It has all these limitations, you know, like we have kind of made improvements. We have like soft body, but like a lot of the stuff in there is still kind of just not ideal, right? It feels like very heavy versus I feel like as soon as I saw Genie 3, I was like, this is basically going to rewrite the entire simulation stack. So like, are things like Isaac Sim and Unity and Unreal, are those just dead on arrival because in 2 years we're going to have basically an equivalent that is based on pure generation like Genie 3, right? Like our world model is going to be a much more diverse and robust way of generating synthetic data than kind of Isaac Sim and the kind of more classic simulation stack. I feel like they are, right? And we can take some of the learnings in this paper where, right, they talk about diversity being super important here. Synthetic data must be well designed. More beneficial use at seed data, right? So what does the concept of seed data look like for sims? It's actually very complicated to do that, right? So like if you have a real robot, in order to kind of use that as seed data for the simulation, you basically have to figure, okay, well, I'm going to figure out where all the objects are, and then I'm going to basically kind of put these things in the scene so that they're kind of about in the same place. But imagine how much easier it is to create synthetic video data from a seed using a world model, right? So if I just have a video recording of what my robot is seeing, I can just feed that into Genie 3, and now I've effectively have a much easier way of generating a lot of kind of possible synthetic data of what my robot was doing, rather than kind of having this thing where I have to kind of like construct it myself. So I don't know. I don't know if I'm necessarily making a ton of sense here, but to me, it feels like there's this kind of tsunami that's coming for the Unities and the Unreals and the Isaac Sims of the world that is basically these generative world models. And generative world models with a seed data of real robot data might actually kind of effectively obsolete this entire simulation stack. I don't think things like Genie 3 will ever be as computing efficient as classical simulation. That's a good point, Julien. What Julien is saying is that these type of simulations, they're also now at the point where they're all basically GPU parallelized. So pretty much all of these can now render multiple different variants on the GPU in parallel. So it used to be the case that simulation was very kind of like single threaded, right? Like you basically had like one simulator and it generated one episode, right? But now all of these simulation frameworks allow you to generate like 100 at the same time, which means that you can generate 100 times more data. So now these simulators are popular because you can generate absolutely massive synthetic data sets for robotics. But yes, that is more efficient than something like Genie 3, but I think Genie 3 gets there too, right? I think eventually Genie 3 can also be done in parallel, and they also keep distilling the models, right, and making them better and better. So like at some point, there's tiny little Genie, or maybe like Genie 6, right? Like the Genie 6 model will just be like this tiny little model. You can run it in parallel, and you give it just one seed of your original robot data, and then it just generates this massive data set of what that robot would have done in a slightly different environment, or from starting from here going slightly differently. Why hasn't there been MOE for VLMs? One for cropping, one for zooming. There probably is MOE for VLM. MOE doesn't... People get confused about this all the time, but like MOE is not the same thing as... MOE is just like a model architecture, right? It's basically just having multiple FFNs. It's basically taking... If we go back to, here's the nice figure from the Nemotron, right? This one here. You see this FFN? MOE is basically just having a bunch of these FFNs, and then you have a little router that chooses which FFN to go to, and then some of those FFNs are not on the GPU. Some of them are basically not used. That's what the whole active parameters versus total parameters is. It's like, how many parameters are you actually using versus how many of these FFNs were basically just on a different GPU or not used for this particular inference. That's a completely different thing from the cropping and zooming here, right? So the cropping and zooming, these are different tools. So I guess what you're saying, Max, is that maybe if you have a mixture of experts vision language model that is taught to use these different tools, maybe the experts specialize in different tools. So maybe if you use the rotation tool, you tend to use specific FFNs. And then if you and whenever you're using the cropping tool, it kind of uses a slightly different FFN. But I don't think that's how MOE models work at all. MOE Mixtral. I always go back to this paper here because they have a very nice figure that shows this. Do they have some kind of Mixtral of experts right here? Yeah, let's check it out. Yeah, this figure in this paper. No, let's do this one. Yeah, this one right here. This is the figure that tells you. So like what people think is that whenever you're doing a mixture of experts, like you end up using the same expert for an entire, so like if you ask a math question, there's like some kind of math expert, and then you're only ever using that math expert, and then there's like a history expert, but the experts aren't separated on semantic concepts like that. And this figure shows that, right? So these are the different experts. And again, because the mixture of experts is at every single one of these FFN layers, right, you have experts at every single layer. So here they're showing you at layer 0, at layer 15, and at layer 31. So as you go up and down this transformer, right? And you can see that the choice of expert is actually kind of like much more varied, right? So there's clearly some expert that's about these spaces, the tabs here. But then whenever you look at here, like this torch here is red, but then this is green and this is blue. So this is like it's not like one expert that's being used for the whole sequence. It's like there's still a huge diversity of experts. I don't know. Hopefully that kind of clears up some of the MOE confusion. Please keep doing robots. Yeah, I mean, there's some selfishness there because it's like, I'm kind of doing some robotics projects, right? I'm working on TapBot, so for me, reading robotics papers feels a little bit more relevant, but I realize that from the kind of YouTube creator standpoint, doing a ton of robotics papers is probably less appealing to a general audience than kind of being a little bit more generic and doing kind of like more generic machine learning papers like this one here. I'm really confused by Genie 3. Why does it seem so computing efficient compared to classical video models? Why does it seem so computing efficient compared to classical video models? So part of the reason why Genie 3 is probably smaller than for example, let's say like the video generation models, is that these video generation models have a more difficult task, right? So like a video generation model has to generate the entire fucking video, right? So think about it like even an 8-second video, if you were doing that at 30 FPS, it's basically like creating 8 seconds times 30 frames per second all at once, right? So it basically has to generate that entire video, and there's all this kind of, I'm trying to find a good picture here, but think about all the attention maps that are in the temporal domain, right? So not only is there the kind of spatial, like within each individual video frame, but then there's also the kind of like temporal dimension, right? So there's a lot of different variants here, but usually there's some amount of communication, right? Maybe some kind of cross attention that's happening within this temporal domain. So generating an 8-second video that is consistent across all those 8 seconds in just one big chunk like that is going to require a bigger model with more model parameters than something that's kind of just generating each frame as it goes, right? Which is kind of what's happening with these Genie 3 models. It's like generating the frames one at a time, right? And because it needs to generate them at a high frame rate, the model itself kind of needs to be kind of small, right? Similar to how these robotics models, part of the reason why they're not big is because they need to be a little bit fast, right? So you can't just have this giant 600B model that takes forever to do one inference, right? So especially if you need to run it on a tiny little edge device. So with Genie 3, I bet you it's actually smaller than the VO3 model, just because the VO3 model generates the whole fucking like chunk video versus the Genie 3 is just doing kind of like one frame at a time. I wouldn't be surprised if Genie 3 has a hybrid architecture kind of like this, right? Because this is already the case for robotics OP3. OP3 robot soccer paper. This one. Oh, I'll get there. Give me 1 second. PDF. Yeah, this one here. So like, this is the robot soccer paper, but if you go all the way to the bottom here, they tell you the model architecture. Oh, where is it? Where is it? Where is it? Tell me. I totally had it somewhere. I remember seeing it. All right. Is it this? Either way, I'm not going to find it, but this is a similar kind of task, right? Where you basically have to generate an action giving observation input at a fast frame rate every single time, every single frame, right? So you don't have to generate a whole sequence of trajectories. You're basically just generating the next trajectory, which is kind of what happens with this, right? It's like it's not generating the whole kind of like front-facing sequence. It's kind of generating just the immediate next thing. And whenever you do that, having kind of a hidden state, right? These Mambas and these recurrent architectures really, the benefit of these is that they have this fixed sized hidden state, which is kind of like a memory, right? That you can run it infinitely, right? So you can run this Genie model, right? If it was transformer and attention based, at some point, right, the sequence length gets so big that it has to cut out the old stuff, right? It has to just get rid of the old stuff. Versus these recurrent kind of Mambas, they never actually have to get rid of the old stuff, right? They always have that little hidden state and you're just kind of overwriting it. So eventually the old stuff will kind of get overwritten by new stuff, but that hidden state is much more capable of keeping old information there. So whenever they do this, the Genie 3 paint persistence. Yeah, this one here. This was like the most insane Genie 3 one that I saw. Let's see if we can get it. Let's go to videos. This one. Yeah, this one right here. So you're painting, right? This is Genie 3. And then you come over here. Okay, you're painting, sure. First of all, the way that the paint, like that right there, is extremely impressive. But the most impressive part is this. Okay, so boom. You look away, and right now, there is nothing inside this image which is keeping the information of that paint that is here, right? So the knowledge of that paint is now inside probably the hidden state of some kind of part of the Genie 3 architecture. So it's all in some compressed latent space, right? Okay, it's gone. Like, it's gone for multiple seconds now. You haven't seen it for multiple seconds now. And then you turn back and it's right there. So that is crazy. That means to me that like the Genie 3 model is storing, has knowledge of the changes you've made to the world. It has a model of the world inside the hidden states of probably some kind of Mamba-like thing. So, yeah. If I look at my foot, then I look away and look back at my foot will change. Makes me think of ring attention. Yeah, ring attention is like another kind of trick, you know? It's like fundamentally, if you're using a transformer, not specifically the attention in the transformer, right? You're going to have to do something because this is going to keep increasing in size. So you can maybe do some kind of RAG thing where you're like storing information in like actual explicit cold things and then you're like pulling it in. There's ways to increase the attention, right? You can, but ultimately the longer the task is, right, the more these kind of Mambas and recurrent architectures benefit, right? So for things like robotics, where you have a robot that's just like running for hours and hours and hours and hours and hours, right? Having this kind of infinite scaling because your hidden size is always the same is a very good architecture, right? It's a very good bias for that particular task. And Genie 3 is the same way. It's like this task of just kind of like infinitely generating a world one frame at a time, but then still having kind of some memory of what's been there. I think these are very good architectures for that. Are they masking a panoramic view or is it memory? That's another theory. So another theory that I've seen is that there's some kind of like Gaussian splat, right? So let's actually go to my favorite Gaussian splat, which is this one here, right, of my latest tap bot. So this is my latest tap bot. But like you can see here how this is explicitly storing information in 3D space using these splats. So some people have said that maybe there's an element of that here, where maybe what's happening is that the Genie 3 model is more like a combination of a model that kind of continuously updates this 3D splat. So it's not that this paint is stored inside the hidden state of some kind of Mamba, but instead the paint is being explicitly stored in a Gaussian splat so that even when you look away, it's still there. It's still like physically there in some kind of physical kind of spatial representation like a Gaussian splat, and then you have a model that's just rendering the frame based on this kind of explicit memory and has some way of basically overwriting specific parts or gathering specific parts. But I don't know about that. That just seems really complicated. I feel like it's probably just like, if I had to guess, I think it's a Mamba or something like that. But I don't know for sure, right? I don't actually have any secret insider information, which is why I can speculate. I think they mentioned, this is Josh, I think they mentioned consistency fades after a few minutes. They did an hour-long dive on machine learning street talk. Actually, that's a good data point. So if they say, here's one way to determine. So if this was a transformer with an attention like this, and then you basically had the history being fed in as a sequence, at some point, this paint would be far enough away in time that it would basically get clipped. So like there would be this discontinuous point where suddenly the knowledge of that paint is no longer in your sequence, and then suddenly it disappears. So like it's kind of like in a video game where like there's objects that are being stored in memory, and then if you go to a different room and then you come back, sometimes you will trigger a kind of a despawn event and that object is no longer in memory, and then when you come back the object is just gone, right? But what you're saying, Josh, is that it's not like the paint disappears, it's like it fades, it like becomes worse. And what that tells me is that that's being stored implicitly, right? So if the knowledge of that paint is being stored inside some compressed representation or some kind of implicit way, then rather than it just kind of suddenly disappearing, it basically becomes more degraded over time, right? So like if you went into the other room and came back, maybe it like forgot about this, but it still knows that there's two big blobs, and then you come back 10 minutes later and it kind of just has one blob because it's just kind of compressed that, right? Because it's like the way that these Mamba models work, right, is that they're like cramming information into this hidden state, and that hidden state it's a limited size, which means that you're kind of overwriting it, right? So like at some point you're going to start, the information is going to like degrade away, almost like diffuse, like kind of like whenever the Thanos snap, and then people just kind of disappear into mist. It's like the same thing is happening inside the hidden state. So you're kind of like slowly forgetting about things rather than just kind of like arbitrarily deciding that's no longer in the context and now it's disappeared. Would models need something to ground themselves? Context will not be enough. I was thinking training 3D space LoRa is maybe on the fly. I'm not 100% sure what you mean there. LoRa's are just basically a little chunk of training that you can basically save to a file and then apply to a model on the fly. So you can have LoRa's for anything, like an image diffusion model, a video model, a text model, a robot vision language model. There's like LoRa's can be put into any different model. The generative world models are kind of like imagination, not simulation. That's a good point, but what is simulation and imagination? Aren't those kind of the same thing? Imagination is simulation using your world model, right? So every human has a world model in their head, right? And whenever you're imagining, you're just using the world model in your head. And the world model in your head is like really fucking good. Like when you think about dreaming, right? I don't know if you guys have ever tried out like lucid dreaming. That world model is extremely good. Like I remember one time I was lucid dreaming, and like this took forever, right? I spent like months beforehand doing like the dream journaling and the like hand checking and all these different tricks to lucid dream. And I finally got a lucid dream, and I managed to like kind of not immediately break out of the lucid dream. And then I was like, all right, let me test out this lucid dream. And I was like, I basically like instantly generated this giant pyramid that I stood on top. And then I instantly generated this giant cliff that it's just like, I could basically teleport myself wherever I wanted and generate whatever I want, which was pretty fucking crazy, right? Because all of that is basically just the world model in my head. So the world model in your head, which is you're using for your imagination, is incredibly powerful, right? And that's basically what Genie 3 is. It's like a version of that. How was the control connected to the model, specifically the action to open the door from the video, so there was no explicit conditioning? Yeah, so the action space for Genie is basically it's kind of like the latent action space. There was a paper that we read. I forget which one it is, but it's not explicit, right? So that's why you can have like kind of weird things like open the door, right? And it's not like actually like moving the hand in such a way that it grabs the door. It's like, it's not doing it at that granularity. It's just like this like kind of amorphous kind of like latent action space where like as you stand in front of something, like it kind of like knows what to do with it, right? And it's just kind of doing what would naturally be done with that thing, but there's no kind of like explicit notion of like, I'm coming here and I'm like touching the specific door handle. Like whenever you use like something like Isaac Sim to open a door, it's literally like looking at the contact forces between the fingers and the actual cylinder that represents the door handle, and then calculating all of those forces together to then get a specific force that is being produced to then hinge the door. It's like all of that is being done explicitly. But whenever you open a door in Genie 3, it's just magical blobs of compute just kind of creating what looks good to you. All right. I'm kind of starting to run out of steam. I think that's pretty much everything I had. If there's any more questions, if not, I'm going to do a little quick summary here and then probably end it. All right. So today's stream was called Scaling Synthetic Data. We mainly focused on this paper. This is the entree of our stream. It's called Beyond Web, Lessons from Scaling Synthetic Data for Trillion Scale Pre-Training. In this paper, very nice, very well-designed paper where they basically go through a series of experiments that they did using different types of synthetically generated data within the text modality. And these experiments kind of paint a picture for you as what is important when you're creating synthetic data sets and what is not important. So I would say that the big learnings from this for me was that there is a lot of benefit to rephrasing data and kind of augmenting what I call data augmentation in text space. So there's a lot of different types of doing this, but things like rephrasing, summarizing, format transformation, content restructuring, there's like a million different ways of describing it, but basically usually you're taking some chunk of text, what they're calling seed data, which is basically just original human generated data, and then using that as the seed for a bunch of different kind of synthetically generated versions of that, right? And usually you're using you can do that either heuristically, right? Like some hard-coded human algorithm to change that, which is kind of what this paper was. Dupo is basically some kind of like weird, like human-designed way of taking one math question and turning it into two math questions. So it's like data augmentation, but in this weird kind of like mathematical way. But another way of doing that, which I think is much more scalable, is this idea, and much more applicable to a wider variety of data, is this using a model to rephrase, right? And they try different sizes of models, and they see that there's actually a correlation here where the smarter a model is, the better it is at rephrasing or augmenting existing data sets in such a way that you can pre-train faster or pre-train and get to a point where the model performs better at a wide variety of benchmarks, right? So synthetic data generation is a capability that scales with model intelligence and model size. So one, to me, that means that there is no wall, right? Well, there is a wall, but the wall is not a data wall, right? So there's lots of walls that are preventing progress and slowing down progress, but data is not one of those walls, right? Some people think that, oh, we've run out of internet data, so we're hitting a wall because there's no more internet data. No, that's not the case. This paper and the other papers that I've shown you make it pretty clear that you can basically synthetically generate data sets. That doesn't mean that there's no wall, because now the wall is just compute, right? It's compute and GPUs and energy, because basically if you have 1 million GPUs, you can generate infinite data. If you have 2 million GPUs, you can generate 2 times infinite data, right? So it's like you're now no longer limited by the amount of internet data. You're now limited by how many GPUs you can use to basically generate synthetic data. So there's still a wall, but the wall is basically just GPUs and power rather than actual internet data. Yeah, so I mean that's most of the paper there, and then there was the one kind of super interesting question that has me, or that this paper has me asking, is like, how far can you get hill climbing on this, right? If you train and create a reinforcement learning kind of environment and system and loop that creates a very tiny model or even a bigger model that gets better and better and better at this type of like rephrasing and text data augmentation, what is the ceiling there, right? Can we get to a point where, for example, here, even with just their 8B model, they generated a data set that is basically 7 times smaller than Red Pajama, but gets you to the same point as Red Pajama? How far can you take that? Could you get to a data set that's 100 times smaller than your standard pre-training data set and it still gets you to the same point, right? Like, how far can you take that? And then what happens when you take that model that is extremely good at rephrasing and summarizing and condensing kind of sloppy pre-training data into this very nice curated synthetic data? What happens if you then apply that to teaching humans, right? Are we going to see superhuman teachers, right? What does that look like? So we also looked at this one, but pretty much all of these, like, I didn't really focus on much other than just the synthetic data aspect of these papers. And I think I just kind of wanted to show you that synthetic data is being used in everything from robotics to math to image and VLM. So it's everywhere. And I think it's good because it means we basically don't need, there's no data wall. There's just a compute wall. Okay, we have some questions here. Ajas, didn't we realize a couple years ago that the quality of data is more important than quantity? Yeah, people have known this forever, you know. Like, you could probably say that people were aware of this hundreds of years ago. You know, hundreds of years ago, people could say, okay, well, this book is smaller than this book, but if you want to learn like calculus, this book is better even though it's smaller. So people already kind of intuitively understood the idea of like higher quality data and lower quality data. But this is kind of a more empirical, like, here's the data that shows that this is true. OpenRoom XYZ, the action space is emergent. You're talking about Genie 3. I wouldn't necessarily say like emergent, where like, yeah, maybe emergent's a little bit too strong of a word, because it's like you're kind of deciding through the data what the action, like why does every single Genie 3 model have the kind of this notion of an action that is move forward, right? Like there's always this kind of like move forward, no matter what. There's this kind of very immediate kind of like move forward action. Well, that's because it's a very obvious thing to conclude. So it's like the action space is emergent in the sense that there's kind of natural actions in your data set that then make a lot of sense to be actions. But it's not emergent in that it just comes out of fucking nowhere, right? It's coming from the data set. Question by Urona. Is there any way we could leverage Genie 3's tight user feedback loop to improve consistency? I don't know if you could like, so there isn't really a tight user feedback loop, right? Like at some point we're going to have neural links in our head, and the neural link in your head will be able to understand and look at your visual field and say, hey, actually the human is noticing this corner over here, and it's taking them out of the moment because they know that this corner doesn't look real. So therefore we should improve that corner, right? So like, but we don't have that type of dense feedback. You know, the best feedback we can get from something like Genie 3 right now and people using it is just like kind of more binary, right? Where they're like, did you like that simulation? Yes. Did you not like that simulation? No, right? Like, so I think that's the type of feedback that we can get from these simulators right now. But in the future, we're definitely going to be able to get kind of a more dense signal from people using these type of world models, because they're going to be able to, maybe through eye tracking or some kind of Neuralink interface, provide a more dense feedback. Would this final data set just be logic? This is Icky Phoenix. I don't know. That's kind of I posed this question because it's super interesting to me. It's like, if we train an ASI model, ASI in rephrasing, and then say, okay, condense calculus down to one page, what does that page look like? Right? Like, what is one page? What is human history in one page? What the fuck does that look like? I'd love to know. We have trained 0.5 billion model with 100 data points to train for behavior we want perfectly on top of pre-trained. 500M with 100 data points sounds a little bit overfit, but I meant to control input move forward frame by frame. The page is just pictures of cats. Is this cats? Standard model? Standard model of physics? Is that what you're talking about? IDK. I mean, if you want to get super crazy, like, I kind of think we're already in a simulation. You know, I think this is the reality. I think we're in a simulation. You know, we're in basically a super advanced version of this. If you compress everything, then you get some kind of standard model of physics. Kind of. And like, I think the important thing there is that when you compress, you lose, right? So it's like, compression almost always results in like degradation, right? So the same way that you keep compressing things and at some point you start to lose resolution, that also applies to world models. So if you keep compressing kind of our knowledge of physics into just like a set of equations, those set of equations are no longer perfectly predicting every single part of our world because they've kind of lost some of the nuance because they had to be compressed into that very small set of equations, right? So I think that's part of perhaps a wrong intuition with the current model of physics, where it's like there's this kind of assumption in physics that you can basically reduce everything to just like a little equation, and that equation will apply to every single thing at every single point in the universe. But that just doesn't seem necessarily correct, right? It could be the case that the more you kind of compress something into a little equation, the less relevant that equation becomes, right? And it'll never perfectly represent everything because it's just you're forcing it to be compressed into this tiny thing. The standard model predicts the universe, but it's very hard to run and needs a lot of GPUs. Yeah, now we're starting to get to the notion of computational irreducibility, which I think is a really great concept, where at some point, if you want to do something or compute something, there's like no compressed way, like shortcut of getting there. And maybe that's, we start hitting a wall for this type of ASI and rephrasing superhuman teacher, where there's no way to summarize an entire calculus textbook into one page of text that'll get you to the same place, right? Maybe we start getting to a limit there, but I don't know. We have to try, right? All right, that's pretty much it. I'm already over, but Mandelbrot set, totally deterministic, but yeah. Fractals are the answer. Is that what you're saying? I don't know. I don't know about that. We're getting too metaphysical here. I'm going to go back to my Gondor horn. All right. Thank you, Ajas, Open Room XYZ, Josh Phillips, Pratyush, Eurona, Julien, Google Account, 87GN, Ed, Max, Saskia, sorry if I miss your name here. I'm just trying to scroll through here. Steak, Mark B, Pratik. Thanks everybody for hanging out. Hope you guys had a great time and hope you guys have a great weekend. And see you guys later.